Yeah, I think it's right. Okay. Hi guys, how are you doing today?
Hello.
Hey. All right, so you guys willing to come to the lecture on Monday? That's very good. So, do you guys watch the YouTube video? If you didn't, please watch the one. So we're gonna move on to the little bit later part of the chapter one. So we're gonna do a little bit of review on Jenkins 1 and 2 chemistry before we hit the actual organic chemistry. So the last time, I'm also gonna briefly review. Okay, so we talked about some orbitals. Okay? Talked about the orbitals. So we briefly talked about the quantum numbers, how it works, and finally, you have to know about how it works, especially when they try to make a covalent bonds, right? So whenever they do, mainly we're gonna talk about the carbon and hydrogen, right? So let's try to see what they do normally and the compound in a molecule. So whenever they try to make the bonds, the carbon once again is group 4. So there's 4 available valence electrons they can use for making new bond. Okay. So if there is some type of bond here, okay, you think of this one. And we find out that all bond lengths and bond strengths and everything was pretty same. So we actually find out this was hybrid orbitals, right? So pretty much the only thing you really need to remember is this one. So whenever you have a single bond, maybe to the hydrogen or carbon, it doesn't really matter. So if it's a single bond, you're going to have a hybrid orbital coming in and make a bond, but it looks like there's one sigma bond over here. So if it's a single bond, there's only one sigma bond. It's simply because what it looks like when you do hybridization of the orbital coming. Okay. If there is a double bond, okay. There's going to be one sigma bond, okay, plus one pi bond. Okay. So please remember this one, okay. And then if there is a triple bond, okay, it's a triple bond. Just the one. So always there's going to be a sigma bond here. There will be 2 pi bonds. Because the double bond that has a pair of electron in each carbon or each elements that has in a p orbital, making pi orbital here, and there's actually 2 more. So there'll be 1, 2. So 2 pi, and also there's a sigma bond in the middle too. So it's really hard to see in this overlap. So that's why if you use the single bond for carbons, for the sigma bonds, they're going to have one. This is sp3, because they're all 4 electrons are hybridized in the same hybrid orbitals. But this is going to be sp2. Okay. That's why there's a pair of electrons. Well, 1 for each p. There's 2 on p will make bonds. That's why you're going to see the single bonds and double bonds and triple bonds made of different types of other bonds. Makes sense, right? Okay. So if that is the case, why it's so special is that the nature of those bonds are quite different. So if you think about it's quite obvious that if you think about the bond strength, or you can say bond energy, bond enthalpy is pretty much the same, how strongly those bonds are made. And you can think about the bond length as well. Okay. So obviously, the bond strength, this is the strongest. Okay. I think This was about 840 kilojoule per mole. And double bond is the second strongest, obviously, because this is 1 pi 1. So this is the second strongest. I think it was 614 or something. Okay. And then the single bond is the weakest one, right? Weakest one. So 347 kilojoule per mole. But the only thing you really need to know is not the numbers. See, it's kind of common sense that this might be the strongest, second, the weakest. That's what you need to know. Oh, so if that is really true, so once again, you don't have to know the numbers. That's fine. But whenever you try to get the bond length, it's actually kind of vice versa. So if they are strongly bound to each other, it's quite obvious that they will actually get close to each other, right? When they're close to each other, they're going to be strongly bound to each other. So this is the shortest one. Shortest one. It's about 120 picometer. This is second shortest. You can say second largest among three. It's up to you guys, but just relatively speaking, you know what's the point here. Okay. So once again, you don't have to memorize the numbers. There'll be too much to memorize, but just make sure which one is the strongest bond, what might be the shortest bond length among those three, might be the best job for making sure, oh, this might be certain reason where you see the carbons are quite close to each other and so forth. Okay. So this is kind of a reason why we want you to know when you look at the compounds, they're mainly sometimes made of just all single bonds, but you may sometimes see the double bonds and triple bonds, and we're gonna learn how to name those three with the maybe other possible functional groups. We're gonna cover that too. Substitution groups and the chemical nomenclature later this semester. But this is a kind of a nature of the three. So normally we kind of put them in one nice way to put it. It's a bond order, meaning it's very simple actually. So bond order simply means numbers of a pair of electrons. So if there's two electrons are involved in bonding, which is a single bond, right? Then there's one pair of electron, right? One pair of electron are used to make a bond. So bond order of single bond will be 1, because there's a one pair of electron. But double bond, obviously not 1, but 2, right? So they're going to be 2 pairs of electrons are used for making double bonds. So bond order for double bond would be 2. So for the same reason, we're gonna say bond order of triple bond would be 3. So we know there's 3 pairs of electrons, means 6 electrons are used for making a triple bond. That makes all difference in bond strength and bond length. We can simply arrange them in order of bond order, which is 1, 2, 3. Simply numbers of pairs, electron pairs. Okay. Perfect. All right. So makes sense, right? You good? All right. Perfect. So I appreciate this is pretty much something you have learned in J-Chem 1 and 2, and also a good reminder. But it is important to always review what you already done before the actual organic chemical learning. So to do this quite a time, people be heading. So let's do a bit of a practical time. Okay, let's do a little bit of practical time. So if I put this in the exam, right? What kind of a possible problem you may see on the exam or the quiz is will be this one. So if I before I get to that one, I'll show you some Lewis structure. Okay? So maybe this one is called methane. Okay? So there's a certain names I want you to remember, to memorize. is only 1 to 10 carbon chain nomenclature, meaning maybe you don't have to do it now, but eventually I hope you can get used to use those terms eventually. So this is math, this is F, and prov, build, and hex, F, up, none, dig. Okay, so those are the ones actually tell you how many carbons are there in the longest chain in your compound. So obviously, if you look at this CH4, they only have a 1 carbon in this organic compound. So there will be 1, so it will be 1. If there's a 2, it will be this 1, 3, 4, 5, 6, 7, 8, 9, 10. You don't have to know about the ondecan, dodecan, or icosane, tricosane. You don't have to know. Only thing that I want you to know is only 1 to the 10. Then you're fine. Don't worry about anything else longer than 10 carbon chain in organic compound. So this is not something I just want you to memorize right away, but eventually over time, it would be great if you can just naturally learn those nomenclature over time naturally. Okay. So anyway, if that is the case, I'll just keep that for a while. If that is the case, if I give you 2 carbon in a chain, and I'm going to fill the hydrogen because the carbon once again is group 4, right? It's group 4. So we're gonna we actually mean this by saturating carbon. So if you guys sometimes look at the nutrition facts on your food products on the back side of your package, you always see that the nutrient facts, you sometimes see the saturated, unsaturated fat indication. That is part of that because most of the fat is mainly organic compound. It's just long carbon chain. So meaning if 2 carbon has to be fully saturated with hydrogen, that's why because they have a 4 valence electron, so we're going to fill that all with the hydrogens. So if you do that, this is also Jenkin 1 and 2. If you have a CN, if it's fully saturated, it has to be H2N plus 2. Okay? So meaning if you have a 2 carbon, it has to be 2 times 2 is 2N plus 2. So that's why I'm sorry, 6. So that's why it has a 6 hydrogen around 2 carbon in the compounds, right? So this is something you can remember too. If there's a double bond, it's 2N. If there's a triple bond, it'll be 2N minus 2. But for now, we'll just stick to this 2N plus 2 for saturated, fully saturated organic compounds. So if that is the case, you could possibly think there's a how many sigma bond between carbons? Okay? If that is the question, right, then you don't have to worry about the carbon and hydrogen bond, right? So this is a carbon, hydrogen, carbon, hydrogen, carbon, hydrogen, carbon, hydrogen, carbon, hydrogen, carbon. So you don't have to worry about this one. Most of the time, we only care about how those carbons are linked together. Okay, so normally we don't worry about this one because it's there has to be just as hydrogen. We all know that, but carbons may be different because if you look at the periodic table, carbon is in p orbital box, right? Before you hitting the p block, you're going to hit the 2s first and then 2p. So meaning, if you look at the carbon or oxygen or nitrogen, they are able to do triple bond or double bond because they're in the p block. But if you look at any compounds in s orbital, they cannot do the double bond or triple bond because this is where they cannot find any electron available on p, which is required for double and triple bond. So that's why if you look at the carbon, so you don't have to work with the hydrogen, they're only going to be single bond. But the carbons, this is where we need to know, oh, it might be possibly double bond or triple bond if that is the case. So if that is the case, you only need to answer me from here, carbon and carbon. So this is only single bond, so they're only going to be one sigma bond. Perfect. That's it. Okay, perfect. If that is the maybe here, okay. If I do this one, okay. So once again, maybe question would be like, how many sigma and pi bond will be there in carbon chain, which is only the ones in carbons. You don't have to worry about their carbon to hydrogen. So in this case, this is a single bond, so we know there will be one sigma bond. Okay, and here it's double bond here, right? So if that's double bond, we know there will be one sigma bond and one pi bond over there. So in total, in this carbon chain, you have two sigma bonds and one pi bond. That will be the answer. So this is something you may see on the Canvas quiz and also the exam. This is type of information we can get for this carbon chain, which might be very crucial for predicting how this organic chemical reaction will happen in your experiments and so forth. So that's why we kind of focus on those bondings. Okay, makes sense, right? Okay, perfect, great. Maybe if I give you this one, can you do this real quick, maybe? Okay. So here, so there'll be 3 hydrogen. There's 1, 2, 3, 4. There'll be 1, 2, 3, 4. So there's no hydrogen actually here, but with 1, 2, 3, 4. I'll get to this one real soon. Don't worry about this one. But for now, if this is the case, how many sigma bond and pi bond will be there? Can you guys guess? So there'll be one single bond and one triple bond. If that is the case, how many sigma bonds and pi bonds will be there? Can you guys guess? There'll be one sigma, another one over here, right? So it'll be 2, perfect. And there's no pi bond here, right? But here will be 2, perfect. Perfect. So in total, we have 2 sigma, 2 pi. That's it, really. You already got the one question right ahead of time. Really, this is really what you need to do. Perfect. So, so that is kind of a reason why if you look at the carbon numbers of carbons, the carbon chain, you can tell methane and propane over here. So this is also type of names that I want you to remember. We'll get to there soon. I think it's chapter 2 or chapter 3. Okay. So if that is only single bond, A and E, triple bond, E and E, Y and E, but we'll get there soon. But there's the one. First, I want you to kind of take a look over time and see and learn those names in naturally. Okay, so I think next one is the drawing. So most of the time, this is kind of a tricky. So I want you to remember this for this semester. So whenever you do the Lewis structure. Okay, so I'm going to do 3 carbons in the carbon chain. Okay. So if I do this one over here, obviously those 4 carbons has to have 4 bonds if there is no double bond or triple bond. So there will be 1, 2, 3, 4. But this carbon, the central carbon has already a single bond to the later carbons over here, so they only have to be 2 hydrogen. Oh, it's not triple double bond, but so there'll be only 2 hydrogen over here. But this is also 3 because there's one single bond to the central carbon to here. So there'll be 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Because they're happy because they're all in group 4 elements over here. So this is one way to draw the propane, right? This is the one. Still, you don't have to know this name yet, so it's okay. But just saying. So there'll be 3 carbons in here, so we call it propane. So this is one way. But normally, if you look at the textbook, they always put the structure in a more like a skeleton way. So this is another way to write it. Okay. So if you look at this, the drawing over here, they're actually going to put each like a dots on this structure, this drawing, meaning there's carbon there. Okay, so we don't write the carbon and hydrogen on this skeleton structure, but you can assume there's each dot on the corner or the end is all carbons. So you can say there's all carbon there. And also, we don't care about the hydrogen in skeleton structure. So this is why you don't even see anything other than carbon here. But you need to assume there are also hydrogen implied there. So it's not shown on the skeleton structure, but what you really look at is the 3 dots. Okay, so in the dot here, and then you can do 3 hydrogen over here. Okay. Well, okay. So this is what you're actually looking at right now. But we only see this one because we don't show the hydrogen on this simpler structure. So this is what we normally do. So if you look at this one, it's same as this is butane, this is carbon, 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 and to the hydrogen. This is what you're actually looking at right now. Okay, so whenever I do this one, I'll do this a lot. Make sure there's also carbon in each dot on the structure, but also implied hydrogen, because the carbon always has to be saturated in a certain way. Normally with the hydrogen, but we're not shown on your skeleton structure. Okay, so this is something I want you to remember here. So if that is the case, now you guys wonder why it's not linear, right? I showed you the linear version here. Now it's like a more bent version over here in each carbons on the chain, because it's very important. So I'm not gonna lie, this will be literally same problem that I'm showing you will be on the exam, on the quiz too. So if you look at the carbon, I do this again, okay? If you look at the carbon here, we actually looking at this methane in 3D, right? But this is the 2D blackboard. So this is the only thing I can do with this one, right? But if you understand, we have all the organic compounds in the 3D structure, right? They're all in 3D. So think about this one. If you have a carbon in the center, if you want to put the 4 bondings in the very evenly distributed on the 3D space, if you do this, what happens? So literally, if they're all bonded on the same plane, what happens to this one is they're wasting. If it looks like a cross, right? Let's assume it's cross. Then if you have a carbon over here, what happens to this one is they're wasting the space on the front and back, because it's not evenly distributed on 3D. It's evenly distributed on 2D, but as you know, we're not living in 2D space, right? So that's why they're actually going to show you some like tetrahedral structure. So meaning, if this is carbon, the one goes up, okay, and then the other one goes on. One goes here, here, and here. So if you try to find the 3D structure of the methane, you can also Google this on the internet. You can actually find there's one is in the here, 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 and here. Okay. So the later time, I'm gonna use some type of a wedge type of drawing and dashed line drawing too. So what it really means is those are the one on the just regular line means they are parallel to this board right now. So if you look at this on the paper in your textbook, meaning this is heading right on the parallel direction of this board or paper. Makes sense, right? So those are in the same plane right now, in this plane right now. Okay. But if you look at the wedge, it's like a dark, wider at the end. Wedge is meaning if this is a 2D, they're on the same plane right now, right? They're on the same plane here and here. The wedge is heading toward you. It's forward, so meaning toward your face, like here. Not literally your face, but somewhere near to your face over there. Okay, I hope that makes sense. And the dashed line is going back. So if you look at this one, it's not on the plane here, it's going this way. This way. So the wedge is going this way. This is going this way. And those are in the same plane of the blackboard. Okay? So this is somehow we can present those structure in 3D using wedge and dashed line. Okay? Makes sense, right? Okay, perfect. So this is not the, tetraplanar, but this is the tetrahedral structure. Okay? So this is why this will be in the exam for sure. It's really important. So each bone angle of tetrahedral structure will be, obviously, average speaking, 109.5. So it's not 90, it's not 120, somewhere between, because tetrahedral structure, it has to be, average speaking, 109.5. And I'll put this on the exam, 100%. I cannot miss this one. Okay, so you need to understand this one to understand why those all organic compounds not linear, right? It has to be all bented. It's also easier for us to look at where the carbons are, but it's really what it looks like too. Okay, so this is why you cannot just put them all in like linear. That'd be the wrong way to put it. Okay, because the bone angle should be here. Average speaking. Most of the tetrahedral structure is 109.5 degree. Let's put that in your head right away. Okay, that's be so great. It's so important number. We need to memorize before we move on. Yeah, go ahead.
So does that mean that all of the bond angles we'll be looking at are 109.5?
Well, if it's tetrahedral structure, most of the time. Okay. But that's a really good question because I'm about to cover the exceptions. Perfect. So. Here's the thing. If you look at one of the things you have to remember from, I think it's Jenkins 2. I'm not sure if it's Jenkins 1. But anyway, you have an electron domain. There are so many other names too, but this is one of the names. Electron domain, electron density, electron reason structure. Okay? So one of them, anything that with the electron structure, is this one anyway, okay? And you have a molecular structure too. So it's a molecular geometry, electron geometry. There are two types of the structure you can look at it because whenever you talks about the structure, most of the time we talks about the bondings, okay? So if there's all single bond and single bond, that's easy question to answer. But sometimes they have a certain element has more than 4 and 6 valence electron, but they're only going to make a 2 or 1 single bond. And that is the time we need to separate them into kinds of a structure. So one is the electron structure, the other is the molecular structure over here. So like I said, most of the tetrahedral structure will show you 109.5 degree for sure. Average speaking. As you know, I'm gonna tell you later, but all the molecules are actually keep moving. They always try to stretch it out and try to kind of move because of that's the intrinsic nature of the compounds and all the elements. Anyway, average speaking, still we need to know about these two because I'll give you one example of water. So water will actually make a 2 single bond to the hydrogen over here, right? Stay over here, but this oxygen is group 6 element, right? So meaning you need to look at this central oxygen. should have a 6 valence electron. But 1 here and 1 here. So hydrogen has only 1. So they make a bond here and here. But that's it. So meaning there's only 1 and 2 electrons are used for making 2 single bonds, right? So there are 4 remaining valence electron on the top of this oxygen right now. So if you have a 1, 2, 3, and 4, right? And if you see a pair of electron after bonding, because they still have a remaining valence electron, we call those, I don't know if you guys remember, lone pair. Okay? Lone pair. And then if you do this one, we kind of consider them as like a bonding. Okay? So in electron domain structure, you count your lone pair as like you assume there's like another bond there. So like this one would have a bond, looks like this, which will be tetrahedral structure. Because you also count the 2 lone pair as a bonding too. But actually the structure, not bonding, but you know what I mean. So in here you count the lone pair plus all the bondings in your electron structure. But the molecular structure, you don't have to worry about the lone pair at all. Okay? I don't have to worry about lone pair, just the bondings. So tetrahedral electron structure over here, but molecular structure of the water is just this one. We call this band shape. It's just the band linear. So if that is the case, even though structurally speaking, this will have a tetrahedral structure. So this should be 195 degree too. But I want you to remember this one. This is not always true, but 95% most of the time. If you have a lone pair, so if you think about the lone pair is not the bonding actually, but it takes a certain space, they fill the electrons in it there to keep those very stable in a stable form. But it's not bonding, so it kind of makes sense that they will take a bigger space. They're more like a wider portion. It's not like this bonding technique is not linear either, but well anyway, the lone pair will take bigger space than the regular bonding. That's the general rule. So meaning, if you have a 2 lone pair taking those big portion of your space around the oxygen, those 2 bonds, regular bond, will be weaker to taking a space, will be more like a squeeze in this way. They're more like a forced in an inner way, right? So those bonds will be a lot smaller than 105. It's be sometimes 106, or 105, it goes on. But obviously, if I put this on the exam, only thing you have to know is, no, wait a minute. Yeah, this is smaller than 109.5. That's the only thing you have to know. Okay, so even though it will show you tetrahedral structure and electron domain structure, if there's a lone pair, all the bonds will be the bond angle will be smaller. Okay, so this is one possible exception you may see. So even though it's a tetrahedral structure, if there is a presence of lone pair, you will experience the smaller number for the bond angle. That's a very good question. So this is something you have to sometimes think about. Okay, I think was it thinking 2? I believe. Anyway, okay, makes sense, right? Makes sense, right? Great. So we have just a bit of a time because I normally finish this one. My plan is, you guys remember, you guys in Wednesday or Friday, Wednesday or Wednesday. So if you come here, your regular class time, you're going to have the bit of an activity, right, for the extra credit. You guys remember this? So I normally finish the lecture in 40 minutes, and this is also my maximum capacity for myself too. So anyway, so I'm gonna finish it. Just one more thing. I'll finish it here today. That is the drawing over here. So if I give you a ring structure, it looks like this. This might be a bit more tricky, right? But we can get to there. And maybe I can give you this one, and maybe I can tell you, oh, what might be the chemical formula of this one. Okay. So it's pretty much the same. Only thing you have to know is, once again, each corner of the dot is carbon, and their hydrogens are implied there. So what you can do is here, carbon, 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 carbon. Okay. So I'm not going to show you on the exam. You need to know where the carbons are by just looking at the corners and the dots over there. Okay. So there'll be 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. You count them, right? 9, right? So there'll be the C carbon 9 carbons over here, and then you can also try to. So if you look at each here, the dot at the end is to be 3 hydrogens. Okay, there'll be 3 hydrogens too, because that makes 1, 2, 3, 4, 1, 2, 3, 4, right? But those who want in the ring structure will be 1, 2, 3, and 4. You don't see it there, but there will be 2 hydrogen on the here. This one is a bit tricky, right? 1, 2, 3, just 1. Because there's already 3 bonding to the carbons. So only 1 hydrogen needed here. Here, 1, 2, 3, and 4. 3 and 4, okay? 1, 2, 3, so it'll be only 1 hydrogen here too. 1, 2, 3, and 4, okay? And 1, 2, 3, and 4. And 1, 2, 3, and 4, okay? So if you count all the hydrogen, there will be the number of hydrogens. So you can count them here. So it'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. Okay? Makes sense, right? So it'll be C9H18. Okay? So I want you to do this every time you look at the exam. No, just kidding. Just kidding. So here's the thing. You can do this way. That's totally fine. It may be handy if you do manually. Sometimes you have a look at certain parts of the organic compounds, the reactions. But obviously, I'm just telling you it's really a lot long work. So what I'm really saying is if you look at the compounds, only thing you have to know is if there is a all single bond. Okay, if that is all single bond, like I said, it's a C9. So the Cn H2n plus 2, right? So it'll be 9 times 2 is 18, right? Plus 2 is what? 20, right? So you can say, oh, there's a 9 carbons, and there's a C2n plus 2, so it'll be 20. So it'll be C9H20. Then it's wrong. You see that, right? So I'm telling you this. If it's the linear, you can do this. If it's a ring structure, you also need to do -2. Because if it's a linear, you have all the hydrogen at the end, 3 and 3. But if you put it into the ring, there's the last 2 carbon linked together with the ring, right? They lose the 2 hydrogen there, because they only need 2 for each, not 3 anymore. So 6 to the 4 is there'll be 2 hydrogens missing. So if it's a ring structure, even though there's no double or triple bond, you still need to do -2 there. So then you don't have to count it. You just need to know, oh, maybe I can do Cn 2n plus 2, but there's 1 ring structure there, so I need to do -2 for hydrogen. So this is for sure indeed the right answer. If you want to double check, you can just do what I just did over here. Okay? That's it for today. Thank you guys. All right.